Greetings to all and welcome to this lecture. We are in module 2 and we are discussing two terminal MOS structure. This is lecture 5, general analysis 2. In this lecture, we are going to discuss about a closed form relation between QC dash and psi s with related to the applied VGB. Meaning, you have a two terminal MOS structure, this is an oxide and this is body. You are applying a gate to body voltage from externally, and ultimately you need to form or you need to formulate a closed form relation between this applied voltage and the internal quantities. So, this psi s is an internal quantity which actually results the QC dash, and then we will discuss about the body effect coefficient also. These are the learning outcomes of the lecture which helps you to explain the mathematical development of general MOS structure. Let us do a quick recap. In previous lecture, we have discussed that the MOSFET structure does have three operating regions: accumulation, depletion and inversion. This completely depends on what is applied gate voltage. If the applied gate voltage is equals to flat band voltage, then there is no charge. So, we said that in flat band condition, the channel charge is 0, the surface potential is 0. We said that if the voltage is negative, it means you are applying a negative voltage to the metal and this results in a positive charge into the semiconductor, and hence in accumulation my charge is positive and the surface potential is negative. This is accumulation condition. Then we argued that what will happen if the VGB is increased towards the positive side. If the gate to body voltage will increase towards the positive side, it will ripple the hole deep in the body and hence uncovered immobile ions will come into the surface. That is called depletion. So, if surface potential is greater than 0 but less than equals to phi f, then you are in depletion. And if you further increase the gate to body voltage, the surface potential will increase. After 2 phi f, the strong inversion or the inversion comes in, meaning the electrons which is minority carriers in the p-type semiconductor will come near the surface and they form a channel, they form a sheet of electron layer near the channel. This is called inversion. Then we started formulating a general relation between the channel charge and the surface potential. By following the junction law, we started our analysis considering as a function of y. So, this was the y direction, this was the x direction. By considering a general formulation of electron concentration, we said that Ny is equals to n naught exponential of psi y by phi t, where psi y is the potential measured from the surface to deep in body. So, this is psi y. This is your metal, oxide, and here the channel charge comes into picture. This is your psi y. We applied the boundary conditions also, considered that after a certain depth the depletion region expansion will stop and this potential is 0 deep in the body, and hence we said that this potential is surface potential with respect to deep in the body. Following the same equations, we started building a Poisson equation and relate the surface potential with the channel charge. We said that the channel charge can be written in this form. Here, if you remember, the first term is due to hole contributions, hole contribution. The second term is due to immobile ions, whether it is acceptor or donor, because again we are deriving or formulating a general equation. So, we need to consider both at this stage, and this is electron contribution. By applying another boundary condition, we solve a general form of equation and came back and get this: QC dash is equals to minus of signum psi s into square root of 2 into q into epsilon s into Na, phi t exponential of minus psi s by phi t plus psi s minus phi t plus exponential of minus 2 phi f by phi t into phi t exponential of psi s by phi t minus psi s minus phi t whole square. This is a general form of equation. Let us plot this equation between qc dash and psi s. It means I am interested to see how my channel charge respond to the surface potential in all region of operation. Again, if you take surface potential in x axis, then surface potential can have some limited values. For example, the surface potential is 0 here, right, which is considered to be as flat band condition. When you increase the surface potential towards positive direction, there will be a point comes in when the semiconductor is equivalent to intrinsic semiconductor. This zone is known as depletion. So, when the surface potential reaches to phi f, ultimately this region is called depletion. After 2 phi f, what will happen? The inversion starts. Let us start understanding different region of operation. For surface potential negative, right, when you apply a negative VGB, the surface potential will be negative and the charges will be dominated by holes. The holes will accumulate near the surface. This region of operation is accumulation. When you applied a positive voltage of VGB or the gate to body voltage, then the surface potential will be positive and majorly the charge will be given by uncovered immobile ions, which is negative. So, the charge will be negative. Now, you go on increase the body voltage, gate to body voltage, then what will happen? Some amount of inversion charge will come near the surface, but majorly the charge will still govern by the depletion charge or the immobile ions charge, and hence this region will be almost flat. It will not vary much with surface potential. It means if you go on increase surface potential or which is result of increasing VGB, the change in charge is very minimal. But after a certain point, which is 2 phi f, the inversion region comes into picture and a strong amount of electrons will come from the body toward the surface. So, the channel charge is given by majorly electrons and hence my surface is heavily inverted. Let us complete our analysis by solving few more equations, because our goal is not to find out how the channel charge respond to the surface potential, because surface potential is not in your hand. The actual quantity which is in your hand is the gate to body voltage. This voltage you are actually applying externally. So, you need to relate an equation or formulation how my surface potential respond to the gate to body voltage and how the channel charge respond to the surface potential. So, we saw one equation or a formulation that how the surface potential and channel charge is related, but we need to make a complete closed form equation which relates the applied voltage VGB with the surface potential and QC dash. To see this, let us complete our understanding on different equations. One is potential balance, which we already know that the applied gate voltage is nothing but the phi ms plus surface potential plus oxide potential. There is another equation which is charge balance equation, so which shows that the charge will be conserved into the system. So, Qg dash is equals to minus of Q naught dash minus Qc dash. Semiconductor charge here is nothing but a function of surface potential, right. That is what it is written here, because when you change the gate to body voltage, then the surface potential is changing. As we have seen that if gate to body voltage is positive, surface potential is positive. If the gate to body voltage is negative, surface potential is negative, and so and so forth. Then Qc dash is also responding accordingly. There is another equation which we can relate the gate charge, right. So, Qg dash can be given by C ox dash into psi ox dash, where psi ox dash is the potential across the oxide layer. So, to use these equations, let me formulate another closed form equation which relates the gate to body voltage and the channel charge and the surface potential. So, we will start with potential balance equation. VGB is equals to phi ms plus psi s plus psi ox. This psi ox can be replaced from here, phi ms plus psi s. This psi ox can be replaced as qg dash divided by c ox dash. Again, this qg dash, it means the total charge which is present at the gate can be replaced by a charge balance equation, or can be rewrite as phi ms plus psi s minus q naught dash by c ox dash minus qc dash by cox dash. If you remember from our previous lectures that phi ms minus q naught by c ox, this is nothing but what? Flat band voltage, VFB, plus psi s minus qc dash by cox dash. So, now we are in the stage where we can relate all these three quantities by a single equation. Here we have VGB, which is nothing but the gate to body voltage externally applied, surface potential, which is a result of applied gate voltage, and QC dash, which is again a result of how surface potential tuned in. So, if we solve for QC dash, we will get this equation. So, ultimately QC dash can be written as minus COX dash into VGB minus V flat band voltage minus psi s. Here the quantities like phi ms, q naught dash, cox dash and Na are known for a given fabrication process. As we have already discussed while discussing the change in the potential balance and charge balance equation, we said that these quantities are fixed. So, if you change the VGB, the change in these quantities will not be observed, because once you fabricate the device, these quantities will be fixed for a given fabrication process. Now, we have two equations. One equation is for QC dash, which is let us say given by equation number 2, and another equation we just saw in our previous slide is this, which is equation number 1, meaning you have two equations and many unknowns, in the sense you have VGB, you have psi s. So, you cannot simply solve this equation analytically, you have to have a numerical methods to solve this. By solving this equation, if you plot the graph, these two equations, so this is the result of equation number 1 and this line is result of equation number 2. How can you plot the equation number 2 on the same graph? Considering, let us consider my charge is 0. So, if QC is equals to 0, what is the value of psi s? It is nothing but VGB minus V flat band voltage. If QC dash is equals to 0, then the psi s value is VGB minus V flat band voltage. Similarly, if your psi s is equals to 0, there is some value of channel charge present into it, which is given by minus of COX dash into VGB minus V flat band voltage. The slope of this line is nothing but COX dash, right, a gate oxide capacitance. Now, as we said that two equations, equation number 1 and equation number 2 shows the same relation of QC dash with psi s and VGB, then the intersection of these two equations will give you the exact value or exact solution, that is this point. Meaning, for a particular VGB, you have a particular value of psi s and that psi s is responding you a particular value of QC dash. Let us take an example. If I reduce VGB, so I am here. If VGB is reduced, then this solution of equation number 2 will give you this line, and hence the intersection point will be this, which is in general, if you reduce VGB, you are going towards the depletion. So, we are in positive direction, but you are actually reducing the VGB. If you reduce the VGB, what will happen? The force, the electric field is not that high, which will actually pull the electron from the body, and hence the negative charge at the surface will only given by the uncovered immobile ions. So, likewise, we can take any value of VGB and find out the closed form solution, which will be given by the intersection point of this QC dash and psi s graph. Again, let us formulate a closed form equation in terms of VGB. meaning how much voltage VGB you are required to cause the inversion, depletion and all, and what is the relation with the channel charge. So if we rewrite this equation from here, then VGB can be written as V flat band voltage plus psi s minus QC dash divided by psi ox dash. If I am going to put QC dash from equation number 1, ultimately what I will get, VGB is equals to V flat band voltage plus psi s, now minus QC dash psi s. In equation number 1, if you see, this is negative of signum psi s into this quantity into this complete big quantity. So I can rewrite here as negative and negative positive signum of psi s into square root of 2 into q into Na into epsilon s into square root of phi t into e to the power of minus psi s by phi t minus 1 minus phi t plus psi s. So this will not come like this, yeah, psi s plus e to the power minus 2 phi f over phi t into e to the power psi s over phi t minus psi s minus phi t, right here, and divided by COX dash, you see here prime, right. This quantity can be defined as gamma. So gamma is equals to square root of 2 into q into epsilon s into Na divided by COX dash. This quantity is known as body effect coefficient. We will discuss about body effect coefficient in subsequent lectures. Here this equation can be written as a closed form equation which relates what is the gate voltage which is in our hand, what is the gate body voltage applied, what is the resultant surface potential and the total channel charge, right. So to make it simpler, we can use some known values like Q, epsilon s. Here epsilon s is the permittivity of silicon, which can be written as epsilon naught into epsilon s. So relative permittivity of silicon is 11.7 into 8.854 into 10 to the power of minus 14 farad per centimeter, and here Q is the electron charge, which is nothing but 1.6 into 10 to the power of minus 19 coulomb. Again this COX can be written as epsilon OX dash into TOX, right, and epsilon OX dash can be again splitted into epsilon naught into epsilon ox, where epsilon naught is a permittivity of air, which is 8.854 into 10 to the power of minus 14 farad per centimeter, and the relative permittivity of the silicon dioxide is 3.9. Considering all those known values, I can get a simple formula or simple equation for gamma in terms of TOX, which is the thickness of oxide, and the body doping. If I am going to plot this graph, we will get that the body effect coefficient varies linearly with these process parameters or with the doping for different various parameters, right. So you are changing the thickness of the oxide and accordingly your gamma is changed, right. So as I said that we will discuss thoroughly about body effect coefficient in subsequent slide. Let us solve a question. It is given as we have a p-type MOS capacitor. P-type meaning we have a MOS capacitor with a body or substrate is p-type semiconductor. You applied a gate to body voltage like this, right. The doping of the substrate is given as Na is equals to 5 into 10 to the power of 17 per centimeter cube. The oxide thickness is given as 2 nanometers. The flat band voltage is given as minus 0.2 volts and the temperature is given 300 Kelvin. The first thing is we need to calculate what is body effect coefficient, gamma. So again we can use a simple formula which is given here, that 0.53 into TOX divided by 10 nanometers into square root of Na divided by 10 to the power of 17 centimeter to the power minus 3 here. So, if we put all those values, we will simply get what is the body effect coefficient, 0.53 into Tox is 2 nanometer in our case divided by 10 nanometer square root of 5 into 10 to the power of 17 divided by 10 to the power of 17. This value comes out to be 0.23 volt to the power half. Now, the second is you need to calculate what is the amount of gate to body voltage required to cause a surface potential of phi f. That is what you need to determine what is the value of VGB which results in a surface potential psi s is equals to 2 phi f. So, first let me calculate what is phi f. We have already discussed in our previous lectures that phi f is nothing but Fermi potential, and this Fermi potential is dependent on the doping of this body, right. So, phi f is can be given by kT over q log of Na by Ni. If you put all those values, this is nothing but 26 milli electron volts log of Na is given as 5 into 10 to the power of 17 and the intrinsic carrier concentration is 1.5 into 10 to the power of 10 for silicon. If you solve this, ultimately the phi f value is coming out to be 0.45 volts. Now, we need to calculate what is the value of VGB. So, I can simply use this equation to calculate the VGB because I know all the value. V flat band voltage is given, or you better use this equation because you know flat band voltage psi s is equals to phi f we just calculated, and keep all those parameters. So, I am rewriting this equation as VGB is equals to V flat band voltage plus psi s plus signum psi s into gamma square root of phi t e to the power of minus psi s by phi t minus phi t plus psi s plus e to the power of minus 2 phi f by phi t into e to the power psi s by phi t minus psi s minus phi t. Right. So, V flat band voltage is minus 0.2 volts. So, let us say minus 0.2 volts. Surface potential is nothing but what? Phi f. So, phi f value we have just extracted is 0.45. So, plus 0.45. Now, if you are applying a voltage positive, right, then surface potential would be positive, or you go like this. If surface potential is positive, what is the signum of psi s? It is positive. So, this will be positive 1. Gamma value we just calculated, which is nothing but 0.23. So, this is 3 here, volt to the power half, 0.23 into phi t. Phi t is what? 26 milli electron volts into e to the power of minus phi f by phi t, because surface potential is now what? Phi f minus phi t plus phi f plus e to the power of minus 2 phi f over phi t, e to the power of phi f by phi t. Here another term phi t will come, right, minus phi f minus phi t. The one way out is you keep all those values in this equation and calculate the exact value. The another way is you can do some approximation, because if your approximation is good, the complexity will be less. If you, so it is a general rule of thumb. It means if you have a good approximation, the complexity of your model will be less. Consider this value. This is a decaying exponential of some positive value, right. So, it can be written as e to the power of minus 4.5 divided by 26 milli electron volt If it is a decaying exponential with respect to this, which is just phi f, you can simply ignore that value. Similarly, this phi t is nothing but what? 26 milli electron volts. As compared to 0.45 volts, 26 milli electron volt is very, very small. So, you can simply ignore that term also. Yes, you cannot ignore this term. This is having some significance. So, this term is also can be ignored because this term is multiplied with some exponent of e to the power of minus 2 times of 0.45 divided by 26 milli electron volts. So, you can simply ignore this term also. Ultimately, you can simply rewrite VGB is equals to V flat band voltage plus psi s plus gamma root of psi s. In case of this equation, psi s is nothing but phi f. So, this is phi f. When you solve this equation by putting all those values, 0.2 plus 0.45 plus 0.23 into square root of 0.45, you will get approximately 0.4 volts. So, that is the total voltage you need to apply to attain this kind of condition, that the surface potential will be phi f and the flat band voltage will maintain a value of minus 0.2 volts. So, let us summarize. In this lecture, we have seen that a closed form equation is very important because we are not only interested in how the surface potential and charge or the channel charge is related. We are actually interested in how my surface potential changes with the applied gate voltage, and in result how my channel charge changes. We have also seen that the behavior of body coefficient, right, gamma, which we are ultimately going to discuss again when we go for 3-terminal MOS structure. We have already seen that the total semiconductor charge and the surface potential is related with a complex formulation. It cannot be analytically solved, so that you need to use some numerical techniques. So, we will stop here for today. Until then, take care.